everyone, we are Lunar Gamers. My name is Jennifer Hars and I'm a master's student in mechanical engineering.
My name is Warner Johnson. I'm a master's student in aerospace engineering.
My name is Ilan Prangler. I'm an undergraduate electrical engineering student.
My name is Pablo Santiago. I am an aerospace engineering doing like a PhD.
Riley Collingford, undergraduate mechanical engineering.
My name is Matthew Davis. I'm an undergraduate computer science student.
Boğaçhan Öndeş. I'm an aerospace PhD.
Oscar Valdez. I'm an undergraduate in electrical engineering.
And our point of contact was Mark Edwards.
So as lunar missions are becoming more complex, they're increasingly relying on coordination between astronauts and autonomous systems. So our team was asked to develop a solution that increases situational awareness on the moon for a continued lunar presence. But before we get started in developing our solution, we had to take into account a few operational challenges. So first, of course, is a damage risk, seeing as the lunar surface is an extremely abrasive terrain. Next, interoperability. There's a lot of moving parts on lunar missions, so making sure they can all speak to each other and communicate clearly is important. Next is radiation. The lunar surface is exposed to intense solar and cosmic radiation, so this can degrade our technology over time. And then finally, emissions info. With everything I mentioned before, this can slow our missions down, so taking all this into account is extremely important.
So for our solution, what we propose is a network of mobile autonomous systems that will provide adaptive coverage with data that they collect. And this will function as an Earth GPS similar yet locally mobilized navigation framework to enable lunar autonomy and position determination.
Over the semester, we've had the opportunity to interview several esteemed space academics, industry experts, and even the opportunity to interview an astronaut. Our sponsor, Mark Edwards, originally gave us a very broad scope, and we were originally going to develop an all-encompassing rover to do many different things at once. One of our earliest interviews with Dr. Crispy let us know that a very broad rover would not likely be successful, that we should narrow our scope, and we did. Additionally, an interview with a technological readiness manager, Ms. Claire Nelson, let us know that instead of using new experimental technologies, we should use existing reliable technologies to again improve our chances of success. We also have a hypothetical budget constraint, and to manage that, we do not need it to be space ready at this moment for testing on Earth as our current prototype. Additionally, we honed in on making mobile cell towers for communication to allow for reliable surface communication on the moon. And also, instead of selling our rovers, we intend to sell them as a service.
So now for some of our critical technologies that a rover would need to perform its functions. For positioning communication, we'll need radio transceivers to communicate data and establish those comm links, and then inertial measurement units for position determination. And next, an extendable antenna to get extra reach out of our data transmission communications. For our power and life cycle, we need solar panels and batteries to power our rover on the moon. We've identified nuclear heat units as a potential up-and-coming technology to provide sustained power and survivability during the 14-day lunar night cycle. In mapping and awareness, we use LiDAR and wide-angle cameras to generate and maintain maps of the rover's surroundings for increased situational awareness, and we'll include a situational awareness display, that way we can communicate that data to astronauts.
As you can see from this table, since there is no unique communication module that can be applied for every purpose, one important aspect that our system should consider is being able to implement different communication modules, such as 5G, very high frequency, or ultra high frequency, S-band, K-band. But an important thing to consider here is that at lower frequency, the further the range that they can cover, but the lower the data that they can transmit. That's why, for example, in 5G, you can see that it can be applied for lunar cellular architectures, but on the other hand, if you want something that can be more variety, very high frequency is the best option. Now, other capabilities that our system should emphasize is being able to detect hazardness in the shape of asteroids that can impact our system, being able to provide communication between the systems, and optimizing the communication data, track path finding, and locate and possible landing zones.
So in terms of our value propositions, once a company leases our lunar coverage system, it splits up into two separate entities. These include autonomous systems with certain missions on the lunar surface and astronauts that will be conducting missions on the moon. So in terms of autonomous systems, we provide mapped operating areas, extended awareness, and precise location for deployment of objectives. This is for more efficient mission planning. And in terms of astronauts, we extend their operating areas, and we also provide safer and more efficient extravehicular activity due to the increased situational awareness on the lunar surface, and precise location for deploying or equipment sampling, and finally, enhanced decision making. And these two entities can converge and provide improved mission success rates, which is our final goal. And so how it works, there'll be a decentralized system of rovers that are situated at high altitudes for network optimization, and this is due to the high altitudes just providing more direct line of sight and just wider coverage.
All right. So now we're going to provide you the demonstration of the things that we accomplish with this decentralized system. The first, well, basically we considered two main courses here. The first one is the wide area coverage, and second one is narrow area coverage, which we will divide later. The wide area coverage, we shoot for the apexes, the highest points around the terrain, to obtain the maximum coverage area with the help of line of sight. So in the schematic we show the logic, and here we're demonstrating our early model of what we now call SWAMPCOM to demonstrate how we achieve the apexes. So the apexes are determined from the existing maps, and the rovers are autonomously climbing to their apexes. So for this system in particular, we're working with grids, and these grids are adaptable. We can change the maps, and the grid sizes will change accordingly. And you can see the grids from the heat maps as well. So I told about the narrow area coverage. So the first thing that we do with our system is the adaptive range coverage, in which case we might have a lower cost for our rovers in terms of power to obtain end-to-end communications, which may not require wide area coverage. And these 2 points might be in remote locations. So in this, as we show in the schematic, there might be mountains between our 2 endpoints. So again, on our SWAMPCOM, we demonstrated with the old model, where we place our rovers equally sized. So just a second. All right, so I'll demonstrate it again. The adaptive coverage, if you can see it better from your screens now. The rovers are equally distanced, and we obtain the end-to-end communications as the heat map provides. Okay, so the second narrow area coverage. So we might be only interested in very small area, and in this case, we might be looking into precision. And to provide precision, we bring more agents / rovers to get better data and the GPS logic. So essentially, we determine a point on the map, and then we place these agents to the certain locations to provide the maximum red area. So all of our algorithms are essentially optimization problems. Okay, so we of course advanced, and now we're going to show our latest model, and in this case we're going to provide you a real moon example. So I want you to guess. Does anybody know which area is this? Well, we actually 3D printed it. We'd like to pass it around. Okay, so Apollo 15 mission. They were trying to land to Mons Hadley, and that's what we're looking at. It's 50 kilometers by 50 kilometers, the area we selected, and this is an automated process. So how do we do it? The LROC is a website. the script takes the data, the map, and then its STL file, which then later sliced into contours to be ready for our software suite. So everything I demonstrated, we're going to demonstrate it again. In this case, now we have numbers. So our grid has 50 kilometers at each unit, and we're going to show you a network that is providing over 95% coverage. And the video doesn't play. So okay. Unfortunately, the video didn't play for the peak apex coverage, but now we're going to demonstrate the adaptive coverage. So in this case, in the early models, we were using equally distanced agents, rovers, but now, as you can see, we have different separations between our agents, and that's due to the A-star algorithm that we use in our model. And our model is also avoiding hazards, which we demonstrate here. They start from the beginning, and if you look closely, there are wiggles in our paths, and that's due to the safety constraints which we included in the optimization function. So, in almost every Apollo mission, we had an issue with the landing, and with this point of interest narrow area coverage method, we are hopefully going to avoid such issues. So now, it's not playing. Unfortunately. Well, I can describe. So the agents are placed around the point of interest to provide real-time knowledge, the distances to the landing rockets, so that we have precision about where we land. In this case, it would be the proposed Apollo 15 landing zone.
So, when designing our rover, we knew that we wanted to make something low cost, since we will be trying to have multiple of these to make up that adaptive coverage network. So, for our inspiration, we used the Chandrayaan 3 rover design, and I made a quick model of it, very bare basics. This is more of a proof of concept, and then we were able to 3D print it, and so we can have a demonstration if you want.
Yeah. So this is like a very small scale model. Like this weighs like 1 kilogram. It's pretty much just an Arduino with an L293D shield that drives its DC motors, and it's controlled by a remote with an IR sensor. It does tank turns, does forwards and backwards, and it's slide. And this will be the preliminary rover cost. It will be around $50,000. Give it more, give it less, depending on the prices of each part. The launch costs are estimated to be $270,000. That is based on Chandrayaan's 3 per kilogram price, which is $43,000 per kilogram, and the preliminary weight will be a little bit over 6 kilograms.
So here's a preliminary deployment strategy that we can see for our rover. First would be phase 1, which is a moon-capable rover prototype. This will be done testing on Earth to make sure that we can actually successfully do our lunar mission. Next phase would actually be practicing the data transfer and the positioning technology of the deployment. Our next phase would be the autonomous climb technology deployment. And then lastly, we would be looking into actually working with our adaptive coverage technology. And then on the bottom here, you can kind of see a Gantt chart of what the next 12 to 18 months would look like if this project was funded and we were able to put this into practice. And that's our presentation. Thank you so much.
Thank you. So at this time, I'm going to put 2 minutes on the clock. Mark, we would love your feedback.
Okay. Everybody hear me okay?
I'm going to turn the volume up.
Yeah.
There we go.
How about now?
Perfect.
Good. Well, kudos to the team. Thought you did a great job. This team has come a long way from the very beginning, and took a very broad problem statement, which was very open-ended and could have had 1,000 different solutions. And I'm proud of them for narrowing down to a particular solution set. I'm impressed by the software prototype. It was unfortunate that it didn't seem to run just as you had hoped, Ochan, but you did a great job of not letting that get you down and distract you and continue on. And you did a great job of explaining it. I love the 3D printed model. You guys pulled that together pretty quickly, rapid prototyping, and so love to see that. Even moves, which is impressive. So I think if I was to provide some constructive criticism and some feedback for you guys to consider for the future, again, I think I know you're compressed with just 20 minutes of time, but try to really slow down up front. It is, especially for those that are remote and listening in, you just got to kind of slow down and make sure that everything is well communicated so that we can hear everything. Unfortunately, with the slides not being shared off the bat, it was hard to kind of follow along in the beginning, so that was unfortunate. But I'm glad we got that fixed halfway through. So yeah, I think just overall, I was very proud of this team for we've met a number of times. They did a great job of reaching out to me, at appropriate stages along the way, and also reaching out to other folks to get their input, other experts. And so I was very impressed by all of that. They were a great team to work with, and I'm glad I got to work with them.